Now, what we're going to discuss is a very important aspect of geometrical optics. What we have is a plane mirror, and there is an incident ray. This is the point of incidence, say P. This is the reflected ray, and this is the normal at the point of incidence. Now, I is a unit vector along the incident ray. That's given to us. So what's given is I, a unit vector along the incident ray. What's also given is a unit normal at the point of incidence. N is a unit normal, a normal of 1 unit length at the point P. N is a unit normal, a unit vector along the normal. It's a unit vector along the normal. We want to find a unit vector along the reflected ray. We want to be able to find the unit vector along the reflected ray. That means obviously we want to find R in terms of I and N. The vector R, which is a unit vector along the reflected ray, N is a unit vector along the normal at the point of incidence, I is a unit vector along the incident ray, right? And we want to be able to find a unit vector along the reflected ray, in terms of I and N. Okay. Now, look, if this is I, then a vector like this is going to be minus I. Yes or no? This vector is going to be minus I. A unit vector, I is a unit vector along the reflected ray. This is opposite to the direction of the reflected ray. This is a unit normal, N. This is a vector along the normal at the point of incidence, and this is the reflected ray, R. Unit vector along the reflected ray, R, right? Very clearly, because of laws of reflection, this angle is equal to this angle, right? That means the vector N is the angle bisector between R and minus I. Is the angle bisector between R and minus I. And both R and minus I are unit vectors. That means magnitude of R is equal to magnitude of minus I. Each is 1. These are unit vectors. And therefore the resultant of these two vectors must be along the angle bisector, right? See, if there are two vectors of equal magnitude, their resultant would be along their angle bisector. Yes or no? That means the resultant of R and minus I is along N. The resultant of R and minus I is along N. So if I write down the vector equation, R and minus I, resultant of R and minus I, what would its direction be? It would be along the angle bisector between R and minus I, which would be N. Why? Because R and minus I are vectors of equal magnitude. They are both unit vectors. So resultant of R and minus I must lie along this vector. That means that must be equal to some lambda N. Scalar times N. Now, so all that we need to do is we need to find lambda. How do I find lambda? Now, I'm going to take R dot N of both sides. R dot N of both sides. See what happens. R dot N minus I dot N equals lambda into N dot N. See, essentially, if I can find lambda, then I would know R. R would be I plus lambda N. So my target, I'm targeting lambda. N dot N is 1. Why? Because N and N are both unit vectors. So that's going to be mod N squared, which is 1. Mod N squared, which is 1. So that is lambda into mod N squared, which is 1. So that's lambda, right? Now, what do I do with R dot N? Would you mind believing? So I have still not used the fact that, this angle is equal to this angle. This is the vector N. This is a unit vector N. This is a unit vector R. Can I not say that R dot N is cos theta? Can I not say this? R dot N is going to be magnitude of R, which is 1. into magnitude of n, which is 1, into cos theta. Can that be said? Yes. And can I also not say that minus I dot n, that means this vector, unit vector in the along the incident ray, opposite to the incident ray, dot n would be magnitude of mod I, which is 1, into magnitude of n, which is 1, into cos theta. Cos theta. Yes. Good for us. So can I not say that r dot n is actually minus I dot n, is actually minus I dot n? Good for us. So r dot n can be written as minus I dot n. So this is minus I dot n, minus I dot n, and that's equal to lambda. That's equal to lambda. That's equal to lambda. So what's lambda? Lambda is minus twice I dot n. Minus twice I dot n. That's lambda. Where I is a unit vector along the incident ray, n is a unit normal at the point of incidence. So lambda is minus twice I dot n. So once I know lambda, I can plug into the value of lambda here in this equation and obtain r. R would be what? R would be I plus lambda n. So here I obtain r equal to I plus lambda n. So I is this, lambda we have obtained minus twice I dot n. So minus twice I dot n, which is a scalar. I dot n is a scalar, into n, which is a vector. That's what we get. So the reflected ray is given by this. So, you know, this is a relationship which you might want to, this is a vector form of laws of reflection, and it can come in very handy. What they could do is, you know, they might just give you, well, a unit normal along the incident ray. They might give you as, or let's say they might just give you a vector along the incident ray, which could be, say, I cap plus j cap is a vector along the incident ray. So the vector I would be divided by its magnitude. You would get a unit normal. You would get a unit vector along the incident ray. And they might give you a normal to the point of, at the point of incidence, and they might say, well, it's 2i plus j is a vector along the normal. So a unit vector along this is going to be divided by root 5. So you get the vector n. And they might ask you to find the vector r. So this is my n. This is my I, and then I can find r from this. I can plug in I as I plus j by root 2, I plus j by root 2 minus twice I dot n, I dot n. So I just need to take a dot product of these two. So this would be 2 plus 1, 3 divided by root 10. So I dot n would be, say, 2 plus 1, 3 by root 10, and then I can multiply it with the vector n, which is 2i plus j by root 5, and I get a unit vector along the reflected ray. Important relationship. Keep an eye on this. Thank you so much. Bye-bye.